Welcome to the fourth week of the DSI Studio workshop. Today we are going to talk about differential tractography and correlational tractography. And let's look at the workshop material on the website. So half of the time today, we are going to talk about differential tractography, and another half will be correlational tractography. So to just recap of what tractography or fiber tracking is doing, if you look at the week 3, there's a diagram telling about the entire workflow of the fiber tracking algorithm. There's a loop here. So during the tracking scenario, DSI Studio repeated doing direction estimation, propagation, and then check termination. So this step have been doing iteratively, recursively until the track terminates. So for most of our algorithm, tracking algorithm, the steps are very similar or even identical. And today we're going to talk about differential tractography and correlational tractography. The entire workflow are identical. So it will be the same for conventional tractography and differential and also correlational tractography, sharing the same workflow. But the only difference that makes differential tractography different is in this step, track termination. So when fiber tracking algorithm, when they want to check whether the tracking should stop or should continue, it will track the anisotropy value. Say if the value is greater than 0.1, usually it will be setting at a very low level, then tracking continues. But as we can see that this low level of the anisotropy will just like map all the pathway, even if the pathway have a slightly injury or damage or degeneration, it will still map it anyway. The reason is like the anisotropy level at the beginning of the disease usually just drop it like 10%, 20%, 30%. But for most of the algorithm, the fiber tracking termination threshold is setting at a very low value. So until reaching the very late stage of the disease, it will only shows up in the conventional tractography. So to cope with this difficulty, we would like to get the tractography more sensitive to the change of neuronal injury. Say right now, if there is a patient have a inflammation of the neuron, the FA drop like just 10% or 0.1. We would like to get that. And the way to do this is to add additional criteria here at the tracking termination. For example, in addition to check the absolute value of anisotropy, we could track, say, if we have a baseline scan and a follow-up scan, we would just compute the FA drop. If the FA drop is greater than 0.1, that we map those pathways, we'll keep that continue. So by adding just one additional criteria, this makes what we call the differential tractography. So go to today's outline. Here's just showing like a brief demonstration of how it shows on different patient case. So in the original study, I picked several of the patients with brain disease like multiple sclerosis, Huntington's disease, ALS, epilepsy, and also control. For all the patients, they have like a baseline scan and then the follow-up. And what DSI Studio did here is, first of all, compute the voxel-wise FA difference. The difference could be small or large, anywhere, or could be just due to the noise. And then using those difference as an additional criteria to determine whether the tracking should continue or stop. And the fiber tracking result was just showing up entirely different. So if we to plot the tractography, the whole brain tractography, you won't tell the difference between all these patients. But just adding this single criteria to say I want to detect tracks with FA drop more than 10%. Then this enhances a lot of different things. Like here, multiple sclerosis patient, they have pathway showing up related to their hyper intensity lesions in the T2 location. And also for the Huntington disease patient, we see a lot of striatal pathway have decreased FA during the follow-up, same as other patients. So this is entirely the entire paradigm of the differential tractography. Just making the tractography different by adding one additional criteria. So let's get some hands-on experience here to see how it really works in real-world data. So let's open DSI Studio. And there's a sample data in the Fiber Data Hub, which would be is my favorite, showing this. And here you go to the repository, open new row, -disease. It may take some time to show it up in your computer, but here you can see that there is a study with a tag of 1378 for SCA to diffusion cancer imaging. This study had been done a long time ago on patients and also healthy control on a specific brain disease called spinal cerebellar ataxia. So this disease affects patients' brainstem and also cerebellum, and they have motor symptoms, difficulty walking, coordinating their movement. And the good things about this study is, first of all, they have control. And then for both the patient and control, they have baseline and follow up. This will be a perfect case to let us study or just the test differential tractography. So here, once you set that this repository, you could look at the node about the detail, and on the right lower corner, you will see a list of data here. And so the subject name started with control. Of course, there are controls, and the patients are underneath listed as CA with subject ID. And they also have section 1 and section 2. Section 1 means it's a baseline scan, and section 2 is a follow-up scan. And here we have 2 reconstruction, which we mentioned in the week 2. The GQI reconstruction get data in such as native space, and QSDR get everything in the MNI space. So to make things easier today, we will mostly just use the QSDR file. So everything is in the same common space to help us to do the comparison much easier. But just let you know, we can also work out differential tractography in the native space. DSI Studio will handle the registration to online subject scans. So first of all, download these 2 data. So baseline scan of a patient, 201, and also the follow-up scan. So set that these 2, and then you can download to a folder. So it may take some time to download, but here you can see what I'm doing with the data being downloaded. Each of them just 1 megabyte, so it should be not taking too long. So once you get the data, you will be looking like this. Will be 2 bit file. One is baseline, one is follow-up. So the idea here, we need baseline scan, follow-up scan, and to get the FA value from one to another. So we could either, first of all, we could open the follow-up scan in DSI Studio. So let's me open up here so I can drag it in DSI Studio. Or you can open it at the first tab. There's a step T3 fiber tracking. So this one is a follow-up scan. And what I'm going to do is to export its DTI FA value. This one is a DTI low B value data set. So today I'm just going to focus on the FA value, which would be more fit for its acquisition. And then I can export the DTIFA from the export menu, click on it, and then save it in the same folder. So right now I have the FA value exported from the follow-up scan. Then the next step is I want to get this follow-up value into the baseline scan. So what I'm going to do, close the window. I'll just open up. You can either drag the first baseline scan in DSI Studio, or either click on the step history fiber tracking and set that baseline scan. And here to get this follow-up data DTI FA value in, go to the slides menu, click on insert other images, and I will set that the one I just saved from the follow-up. So now once loaded in, you will see it's showing up at the bottom of this drop disk. So you can see this was, the second one is the baseline scan FA value. And this one is a follow-up. So we have these two data already here. You will see there's still a little bit misalignment, but it's okay. It will be just coded as like a systematic error, which will tell how to address or like quantify this later. So once we have these two, usually the first step I'm doing is just to test if the fiber tracking is okay, because sometimes there are data quality problem. If you run a simple whole bunch tracking, the results may not be good. So right now, this one is just a conventional tracking results. I just click fiber tracking without changing any parameter. And this is a simple quality check. Make sure everything works. And then I will take this result back. Then I will restore tracking setting, make everything back to default. And then I go to the right upper corner. So in the third week, we briefly talk about some tracking parameter. And there is a list under that's called differential tracking. Expand on this one. And now we expand this one, we see there are two metrics we allow us to select here. If you are using an older version of DSI Studio, the name may be different, but once you update it, it will be the same. And the matrix one, I will select the follow-up scans FA, and immediately DSI Studio will bring it in the baseline. And the computation I want to get is matrix 1 minus matrix 2. So this will be higher than the others, but that's not what I wanted. So I would change this to DTIFA. So make sure you get the right order. If you want to compute to map the decrease of the FA, then here we need the baseline minus the follow-up. So you can switch the order here or change the type here. So you can either use this with this or either change the type. Once ready, there's another thing called a threshold. So this threshold value will be applied to the calculation here. So as you can see, this calculation computes the percentage decrease. 0.0 means is 20% decrease. That's quite a moderate, decent, large value, I would say. And you can immediately hit by fiber tracking, and then it's starting to get some results that showing the decrease of the track in this patient. We haven't changed a lot of parameter here, but you can have a double check. Usually we will have a fixed seeding count. If you're using older version, then you would need to switch to terminate if and set that seeds as the termination count number here. Usually we will put like 1 million seeds, 2 million or 5 million, depending on how much you want to get. And that's the results here. As you can see here, some of the brainstem pathway showing up, and also others pathway are being presented here. So one immediate question we may have is, does this a real change of the neuronal injury, or is just like due to misalignment or systematic error? So one way to check is just to do the same as a control on a control patient. So we can get a healthy control patient if they also have baseline and follow up. We repeat the same process and see if they also show up some of this result. If the healthy control also show this kind of similar result, that means maybe we need to increase the threshold, make it more specific. Or either we could increase the length so that we could get more long range change, which would be also more specific. So for example, I could get this 30% decrease, and then they would get more limited results. Or either I can get 20%, but with longer range track, increase the minimum length, and then see how the result looks like. So it's get a cleaner results and more specific. So I just showing like two common approach to change the sensitivity and specificity. And the key here is we need to do the same on healthy control to see how the result looks different. So let's stick with this parameter, and then we can download the control subject data to see how it looks like. So I'll just quickly repeat what we are doing, but right now I pick control subject, QSDR section, scan session 1, QSDR scan session number 2. Let's just download this too. And once the data get downloaded, I could open the follow-up scan of this control. So it's a control number 1, session 2. Let me export the DTRFA value, save it. Once I save it, open the control subject number 1 of the baseline scan. And then doing the same. So every step just repeat what we have been done on the patient here. Now insert the slides. Now I'm going to expand the tracking parameter menu. So from here, I will match the parameter I used in patient. So it's like 40. The same seeding. For the metric 1, set that the baseline itself DTRFA. And the metric 2 automatically get in the follow-up scan. The type is still the same, 20%, and then get the tracking. So you see, like, even we do this, there's nothing in the control. So that means we can pretty much get very sensitive result, specific result. And of course, we can play with the parameter, say I could allow for shorter length. And now you see some results showing up in the healthy control, but being right away deleted. The reason is there's a trimming action that coming in to reduce some of the noisy results, and it's still getting 0. So say if we don't have this one, or like just like showing a very small value, and it will shows up some of the result. And we will usually treat this as a false discovery, under the sense that this subject is a control subject. And then if we compare this with this, so we're setting all the parameters being the same, and then we get a lot of finding in patient, then most of these results would be true. So comparing these two results, we could also compute something called a false discovery rate. So to get a quantitative estimation of how reliable this result is, one way to do is you go to the statistic, right click on this track, go to statistics, and you will compute the total volume of the finding. So here the total volume of finding is about 12,000 cubic millimeter. In comparison to the control subject, the total volume of finding will be 200. So the ratio of these two values will be quantified as we call it false discovery rate. So total finding here, this volume of the tracks showing up in differential tractography the patient will be here. And then the value of the control divided by the value of the patient, this will be the false discovery rate. Essentially, this tells us the ratio of the false discovery. That means we are treating all findings here as false discovery. And this finding here is a total finding. So the ratio between this divided by this will be the false discovery rate. And usually an acceptable false discovery rate value will be smaller than 0.05. So that's like 5% only of the false discovery. That means we could estimate, if we just compare these two cases, then there will be 5%. Depending on the false discovery rate, we'll know roughly how reliable result we are seeing in here. And if you are doing a study, then you need to apply the same for all the control and all the patient, and get the average finding. So the average volume of the finding in patient, and here the average volume of the finding in control, the ratio will be your estimate false discovery rate. So I'm answering some of the question in the chat here. The first one is, why do I use FA value instead of QA? So there's two reasons. One is this data set is really a low value, low B value data set. If you go to the Fiber Data Hub, usually first thing I did is look at this B value. For B value is around 1,000, is usually very low, and it's not very sensitive in terms of using QA. QA usually will fit for a B value that's higher. And the second is, for the QA, there's a remaining problem of normalization. In all the patients, their anisotropy is like they have decreased all over the brain tissue. So consequently, the QA may not accurately be normalized against with itself's value. So right now, the QA value is calculated assuming that the maximum QA is 1. But for most patients, if they are really have at the very late of the disease stage, they are having all the track having the anisotropy drop a lot across the entire brain. So normalization doesn't really doing a good job. They could accurately normalizing. So due to the two reasons, I found that the QA finding usually that's not really reliable. But hopefully in the future version, we are going to correct for that to get the correct normalization. And once we've done that, we could compare the result of QA and FA. And here the second question in the chat, is there any way to explore the DTI FA during the reconstruction step with C command line? The FA value need to go through the reconstruction. So reconstruction will fit data with the tensor model. So once you fit it, and the FA value will be stored in the FG file. So you have to go through the reconstruction step to get the FG file. The fit file are the data that can give you the DTIFA. So you may not be able to get it from the SRC file during the reconstruction step. So quickly showing how to do this in a longitudinal study. And then you can, if you recall the first week's function of we call the comment history, then you can do this for all subjects using the GUI interface. Just check out the record and comment history. So what I did for just one subject, in the past, we have to write command line to do this. But in the newer version, if you check the first week's tutorial, you will know how to do this for all the subjects. Just check out the recording comment history, then we can do the same for all the subjects. So we did the longitudinal analysis, compare baseline and follow-up. However, for most of the study, we don't have follow-up. We may have only just one scan data from the patient and one scan data from the health control. Then here, the only thing we can do is cross-sectional study. So in the new version, there's a new function. What we can do is, first of all, we create a good average across the healthy subjects and use it as a standard template for comparison. So the first is to average across all the control subjects, and then we can compare patient with healthy control. So to do this, what we need to do is go to a data hub and download all these control subjects data, specifically only the QSDR. So I listed the selection command here. So it's a wildcard. So all the control session number 1, the QSDR, if you copy this and click on select matching, pasting this and click OK. Once you click OK, if you drag this scroll bar a bit, you will see all the control section number 1 QSDR being selected. And there are a total of 16 files, and you just click download. May not take a long time because each file is just 1 megabyte, and just download it. And once we download this, then we can average them together. So as I shown here, we got all the file. Once you download it, you will look like this, all the files being here. In the updated version of DSI Studio, there's a function to average across those control data. It's located within the Tractography batch tab. If you don't see this showing up, that means you need to update DSI Studio. Otherwise, you could just look at what I'm doing. Click on the bottom, click on the add button, and select the control. So here I just skip the session 2 and take only the session 1. And of course, you can also include session 2, just average all of them together. It'll give you more robust result. So click OK. You'll see all the data being listed here. And then just click Create Template. And right now, DSI Studio will collect all the data from QSDR reconstructed fit file, average them, and make sure you download those from QSDR reconstructed fit file, not the GQI, because in the GQI, the subjects in their native space, you cannot direct average them together. So show that file created. Then we can look at the folder. It's creating 2 files. The one we are going to use is the one called ended with mean.fz. Open it up in DSI Studio. And then from here, you can see the average QA value, average DTIFA, average radial difficility. All the average value being here. Then here, we just export the DTI. So right now we have all the controls average DTI values exported. And now we're just doing the same thing. And here let's open this patient data. Let's open up the patient data, insert the slides. So here, instead of inserting the follow-up scan slide, I insert the healthy controls average. And then now I'm just doing the same. But here, metric one, I set that the control FA value. Matrix 2, this subject's value, because we are going to calculate how large controls FA is more than the patient. And just click private tracking. So you will see this showing up a lot of finding in the cerebellum, and it's getting much more results in the longitudinal study. And this makes sense because the longitudinal study only map the difference between two time frames. But before the baseline study, the patient may have been going through a lot of neurodegeneration. And this disease affects mostly cerebellum, and this showing up here. And of course, we could get more specific results, increase the length, or increase the difference threshold from 20% to 30% decrease compared to the control. Then you will get more specific results. So those two parameters are controlling the sensitivity of the finding. And once you get some results, do this the same in the control and calculate the FDR. Then you would have a quantification about how reliable your finding. So let me get to the question in the chat. So can differential tractography be applied to grouped data, data from multiple individual subjects, or in between group studies? Yes, of course. We can even average all patient data together and just run differential tractography. Or either we just average a subgroup. So there's all kind of different way you can average and compare, and the way to calculate the FDR may be different, but you can do this through different experiment design. So all kind of possibility. So we have tools to average data together and just compare one by one. So they essentially, the whole idea of differential tractography is compare one to another, and make sure everything's in the same space. Usually easier to do it with QSDR, reconstructed file, and we could do the same. So in the older version, last year, there's a different approach, which I don't recommend right now, is like we will regress the data against like age or sex or other demographics. But the problem is I try to get an estimate using the regression, may not get a reliable result because those demographics may not be linearly correlated with FA value or QA value of the matrix. This nonlinearity sometimes may cause some problem. An easier way would be just getting an average of them and then compare and then see the results. If there are additional factors like age, like sex or other demographic, we handle that at the end of the statistics. For example, if we get some results using differential tractography, we get some findings from the patient 1, 2, 3, 4, 5, and we can collect all the data. And then here we can apply statistic to adjust the finding quantity based on the age or sex. So we can handle a lot of different variables using different statistic model. But here for getting differential tractography would be much easier just to compare one-to-one baseline to follow up or each subject scan with group average. To finish the differential tractography for the next section will be the correlational tractography. So the entire idea is the same, similar to differential tractography, so differential tractography we track difference. But if we have a group setting, so we have a cohort, patient cohort, control cohort, then we can track correlation. So in group analysis, we may run regression, we may run group comparison. There will be statistic, there will be correlation with age or sex. Those statistics, we could use it as a termination criteria. So similarly, just changing or adding additional termination criteria, then we could do a tractography for the entire group. So here's just showing that example here. We could correlate with age, and then we show a lot of regions showing higher T statistic after correlating, say, for example, the FA with age. And for each voxel, we get a value, threshold it, and run fiber tracking. And we'll get some results. And then we could do the same by after permuting with age. So to get some kind of reliability measurement, one commonly used approach in statistics is called a permutation test. That means we can do the same without permutation to get a fiber tracking result that correlates with age. And then we repeat the same, but here we just randomly permute the age and then see if they get some results. If we see all the results being gone, that means that previously the non-permuted case was more reliable. And otherwise, if we just randomly permute the age, and then we run correlational tractography, and still we can get some results, that means the result we are looking at right now is not so different from random age assignment. So that's the entire paradigm. Similar to what we did in differential tractography, but put in under the group level. And also in terms of the null hypothesis, the null hypothesis in differential tractography is all related to healthy control. So anything we want to compute with any report, false discovery rate, p-value, anything will be tested against a sham setting. The sham setting here will be the healthy control. Usually in the differential tractography, we do that. And in correlational tractography, the null hypothesis will be the permutation. So we randomly permute the age of the sex variable, the group label. Are those findings still exist? If not, then we may be getting a reliable result. So I see a question in the chat. I want to investigate, track correlated with a specific score that is adjusted for age, gender, education, etc. in a cross-sectional study. How can I do this with DSI Studio? Yes, we are going to cover this in today's cross-sectional analysis part. So let's get started. So to do this, first of all, we need to group all the subject data together. And here DSI Studio does is we can aggregate data together. So this is not average. This is called aggregate. So average, you just take all the FG file and sum it, take an average. But for creating, we call the database file. You will collect all the FG file. So the way to do this, if we use the control subject data as an example, we can go to the correlational tractography tab and click on create a database. And here, you could click the add button to select all the subjects we want to include in the database here. And here, I just want to show you a quick example. I just select all the data I have. And here, once you select it, you can select the matrix. Here, you can choose QA. So if you have a bit data that's higher p-value and doesn't involve a widespread and also be decreased, then you can use QA. Or here we just today's study we use the DTIFA, and then just click create database. And it didn't take a long time. Then you create this file, and we can check the database using the step C2. So before we run the correlational tractography, we could look at how this database file looks like. So usually the database file will have a file extension .db.fg. So it's a kind of FZ file, but it's aggregating a lot of subjects data. So click on this one, you will see the data of each subject aggregated together. So when I create this database, I just select 19 subjects, and you will see all of them being here. It's not just a simple average, it's like aggregating all together. And from the Fiber Data Hub, I make things much easier. So most of the study, I create a connectivity database, ended with db.fg. So you just download this one. You can download this file and then check it here. So if you download the one from the Fiber Data Hub, you will notice something different. That's the demographics also being stored within. So you could store this demographic afterward or during creation of the database, or you can replace this. So there are file menu. You can open the demographic. So the demographic will be stored as text file. It can be type separated value or comma separated value. You can see the example of this demographic file in the Fiber Data Hub. It's stored as the TSV, type separated value. You can download this and take a look. The format is very straightforward. And this is the actual demographic file that be imported with this kind of database file here. So you see that this one includes the session 1, session 2, session 1, session 2, and everything will be in and associated. Usually for the demographic file, I will put the first column as a subject ID, and I will check the file name. So this will be like a double check to make sure your demographic match the subject file you have. Otherwise, the follow downstream analysis will be wrong. So make sure this be matched here. Everything's okay. And then we can go to the next step, correlational tracking, and select the file I downloaded from the Fiber Data Hub. So when you open this in this dialog, you will see demographic associated. So this demographic be blended up or stored in the database. If not, you can load it in. So there's a folder bottom. You can open the test separated or comma separated value. Always make sure you have a good match between both. So after you loaded the demographics, you can set that the variable. So when we run correlation, sometimes there are covariates we would like to regress out, like age, like sex. And we can just click on it. If you click this, what DSI Studio would be doing is you would take this and calculate its linear effect with the FA and then partial those effects out. So it's a partial correlation to regress out the sex and age effect on the FA before you study the group difference. So here you could study age correlation, you could study difference between male, female, or we could study the difference between the group. So those are variable setting at this toolbox. And now next one is a parameter, which is having a lot of important things. The one I usually would change is a t-threshold. So this one control whether you want to look at weak effect or strong effect. Lower value, look at a weaker effect size. Higher value, you are going to explore and only look at larger effect size. And there is a length threshold. And remember, this is also a fiber tracking process. Usually higher length threshold give you more specific results. Lower give you more sensitive results. Sometimes you may need to change this into a look at more short range fiber, or either you just want to look at higher range, long range fiber. And you could explore this setting. So you could imagine these two parameters is very similar to what we changed during differential tractography. When we compare baseline and follow-up, we change the anisotropic threshold. That's similar to what you changed here. That's related to termination. Also, there's another threshold about the length constraint, and that's been here. So similar paradigms, but change different name. Then study region, usually I would just assign whole brand. But there's also a way you could include a region. This is a tractography, so you could bring in ROI, you could bring in seeding, you could bring in ROA. But most of the time, we just study whole brand. Unless you have a specific reason to exclude set of balance, exclude a hemisphere, then you can bring in some region from the others and set it as a RA to avoid those regions, or RI you want to study those regions. But for most of the time, I would just stick with whole brand. If you specify region, my past experience is that you will get very few results. A lot of time you would not get any result at all because so constrained. The third tab is also very important, allow us to just set a subset of cohort. So if we don't set any subset, then DSI Studio will compare group across the entire data set. But here we may say, just want to study maybe age greater than 40-year-old. Then I can apply this criteria. Then you will see that some subjects being selected. So these functions allow you to select different subset, or you want to study only male case. So you can add two criteria in, separated by comma here. And you will say that this remaining is a 16. If you just remove all of them, click apply again, then you select all of them. So there's a way you can just select a cohort of it to do the study. In the advanced options, we usually don't change those. The permutation counts determine the total number of permutation will be running here. Usually it will be several thousands, 2,000, 3,000, 4,000. Increasing this will give you more stable result, but they take more computation time. The perming is the same as what the DSI Studio did in differential tractography to remove fragments. So usually my experience is that you don't need to change this unless you have specific reason. Usually this will help improve your final FDR value. And once everything's done, you can just click on this and then let it run. And so here we are study the correlation with group variable. And DSI Studio will run positive correlation and negative correlation. So as you see here, left side is higher FA in group number 1. So if you also can look at this underneath, you're at real time showing you the FDR value. So DSI Studio will at the same time study positive correlation and negative correlation separately and report each of the results. So it's not just testing whether there are increased FA in patient group or in a healthy control group, but also the other way around. And you see here the FDR value need to be just 1. That means there's almost mono finding. And that means and here report did not find track showing higher FA in group 0. So 0 means the patient group. So no higher FA value in the patient group that match what we are looking at here. So you see here, this is Studio assign group variable in this parenthesis. You can check this, and this is the group 0. And the other side, negative correlation is showing higher DTFA in group 1, that's a control. And here in the curve, you can see that the length distribution of the finding is keep running, and you almost didn't see any primitive results. Usually for like study that's weaker effect size, you will see some of the curves showing up after permutation. The primitive result will be more opaque or like more not as saturated color. And here is almost exclusively getting the results in the patient group that has decreased FA. So let me check out the question in the chat. Is it possible to use post-operative EWF for cross-sectional differential tractography? So post-operative, so they will be similar to the baseline and follow-up study. So you can, that's that by definition of the experiment, it will be longitudinal. Cross-sectional means you need to compare two cohort, subject, healthy control. But depending on the experiment setting, you can make it cross-sectional. If you compare post-operative patient data with the control, then it's cross-sectional. Next one, how do you define significant thresholds to identify the region when testing difference in FA in the correlational tractography? So in the newer version, updated version, once you run the analysis, DSI Studio will report the effect size and also tell you whether it's moderate or small. So if you change this, you will see that there's a small effect size, or you want to test it large effect size. So this, as I mentioned, this is additional termination criteria adding to fiber tracking. So this threshold is essentially testing or like mapping tracks with different effect size. If you want to just look at large effect size, increase the T, but you may risk not getting any finding because your study may not have a large effect size. So the the choice of T value, usually what I would do is just like set that different T value threshold, like 2, 2.5, 3, 3.5, and then check out the effect size, and then report each result differently. Because your study could have a large effect size, like this study, the SCA2 study has a very large step size. You can get a T threshold of 4 and still get some finding. But not the case on other study. So usually the good things, try different effect size and run it. And also make sure you can use a lower than threshold, so you get some results even cover the short range fiber. So the answer to your question, how to define significant threshold, the significance here will be reported as FDR, so that's the false discovery rate. Usually it's smaller than 0.05, that's good. The T threshold here is only used to filter the effect size. Next question, why is it not based on Pearson correlation? Because the relation is nonlinear. I found it's much better use nonlinear rank correlation. So the correlation statistic used here is Spearman correlation, is a rank based. The reason is most of the time, the FA value will not be linearly correlated with age or sex or your group variable. It could be a lot of time nonlinear relation. So in that scenario, rank-based correlation would be better. Next question, could you use a tractography atlas in place of a group control? Yes. So you say this, so this, in some study, if you don't have a control, what I would do is go to the Fiber Data Hub and look at study that have similar scan setting as yours, you may be able to use their data as your control. I believe that's possible. So what you could do is, for example, if this SCA2, if I don't have the control data, the first thing I would check two things. One is a p-value. The second is the DWI count. So find study that shares similar setting as these two. And also you can look at the DWI contrast or other quality metrics, see if they are similar. So if you come across a study that shares similar as this, then probably those study you can use it as a template, even a group of control. So for SCA2, the one, if I recall, there's a similar setting in other major study. There's a study that been done also a long time ago called the IXI study. There, so ISI guys, and there is a QC part. And you see they also have the maximum p-value of 1,000. The DWI count is just one more, 16 compared to 15. And if you see the DWI contrast, it's around 1.2, and the neighborhood correlation 0.9, and go back to the SCA2, they are very similar. So if the SCA2, this study, I can just use other studies control and here and justify they have very similar QC profile. Next question. For the correlational tracking results, should we report result with less track? For instance, if I only find one tracking, should I report it or not? I would say there's almost no finding. If you just get one track, it's not reliable enough. So for the example, the result we got here, usually even for differential tractography or correlational tractography, you need to have a decent size of the results. Next question, are there Bayesian statistics approach integrated into DSI Studio? I will explore that route. If it turned out to be more beneficial, I may consider that in the future version. Thanks for the suggestion. Is there a limit to the number of subjects to be aggregated? No, I can aggregate 1,000 subjects. I create like a cartometry database. It depends on your computer hardware. If you have enough memory, you could probably still able to create it. Next one, is this correlational method applicable to lesion study? Quick question is, it depends. If a lesion is pretty large, the normalization may not be right. But most of the lesion study we did seems to be okay. Like stroke study, moderate size of the lesion, probably okay. But it's like the lesion is so large that occupy the entire hemisphere. Usually this may not work perfectly. I would say just give it a try. So finish a cross-sectional analysis and then find the results. So here I just showing you what the results may look like. So after you run correlational tractography, you will get a report in the same folder. Usually how I would do is just go to the HTML file and double click on it and just read through it. It will show you the results in detail. So this one is the patients versus control, and report whether the result is significant or not, and what. So all the figures included here are saved in the same folder. So those folder figures are here. The tracks are here. So you can open this in DSI Studio by opening this FZ file. You can load this FZ file in DSI Studio, and then load in the tracks. And from here, you could do a lot of different further analysis. You can separate some tracks, label it as an anatomical pathway. And then create different figures to visualize the results. So, and also there are a FDR analysis. So usually for longer lengths, it will corresponding to a better FDR. For most of the study, this would be a way you can see if the result is reliable. And this table is also included in the folder. If you look at the FDR distribution value, there's a test file. Open it up, it's actually showing a table. Let's see if I can show. So in this case, it's just the result is so strong, we don't have any finding after permutation. But if there are weaker effect, you will see different FDR value at different lengths. So maybe the FDR value will be even smaller at lengths less longer. So this would 20 means 20 voxel, 10 means 10 voxel. So what you could do is you can, if you find there, you want to report more specific results. Say I want to report some results at a longer 30 voxel distance. You don't have to redo this correlational tractography. What you only need to do is just remove shorter tracks. So there's a function called delete short tracks. And then the scale is in millimeters. So I can say I want to delete those shorter than 40. Then you would just give you a longer range track. And you can look up in this table and see the FDR value of this finding. So that means that you don't, in this, the entire finding, it may include longer range track, a shorter fragment finding, and each different lens correspond to different FDR. And in DSI Studio, you can filter the lens and then just report it, the corresponding FDR here. So last session will be a little bit over time, but this will be real quick. We can do a longitudinal analysis. So here, let's go back to the connectometry database. Go to the correlational tractography tab. Click on the view database and open the one we downloaded from the Fiber Data Hub. So in the file we downloaded, there are session 1, session 2, session 1, session 2. So here, if we want to study the longitudinal change, first of all, when you create the database, make it by this order. So it's the subject number 1, baseline, subject number 1, follow-up, baseline, follow-up. Then go to the tool tab. There's a longitudinal scan. Click on this one, you'll pop out a dialog. And you can see whether it match. So scan 1 is the baseline, scan 2 is the follow-up. And you see that this one match, okay, this one match, okay. So just look at this name, then you can see it's matching, okay. Then here you can change the matrix. Usually we just calculate the absolute difference. So there's a difference of FA value. And there's a drop menu, which we'll mention later, but usually, first of all, we just get no filter applied. That means we'll calculate the difference, and the difference could be increase or decrease. So if there are degeneration, that may be decrease. It may be an increase of integrity, that may be increase of FA in the follow-up. So if you set that no filter apply, then the resulting difference could have positive or negative. And you can set that just to filter one way or around. But here, we just say no filter apply first. So click on this one, then you will see the subject profile change a bit. First of all, the ID is the follow-up minus the baseline. And if you go through, you see some of also turning red, that means decrease. Some of them remain white, means that's increase. And then we can save this as a new database. Then this will be a longitudinal study. So you can save it. Once you save this, you can open in the steps C3, correlational tractography. So the one I said previously, I named it as longitudinal difference. So this one includes both positive and negative difference. And then here, I can test it whether there are decrease of track in patient. So what I'm going to do is I select patient group number 0. That's all the patient group. And here I would test longitudinal change. And at the same time, I can also regress out effects of age and sex. And then run fiber tracking. So right now it's testing whether there are increase of FA in the follow-up versus decrease of FA. So that means here the purpose to use unfiltered result is allow us to use it as a null hypothesis to test it. So this allows us to get some comparison between whether it's decrease or increase. And quickly showing some results reported here. So once this being done, you can look at a report. So track with increased FA, there's none. FDR is just one, so none of the result that has increased. And the decrease is a lot. The FDR value is showing up. So you see a lot of region, not only the one in the brainstem, but also other regions also have degeneration beginning going. And right now, if you look at the FDR table, you can see what I mentioned is that usually for longer lengths, the FDR may be smaller. We may get more specific results. And also, but we'll also get fewer findings here. And there's a button here called View Results in 3D. If you click this one, DSI Studio just load the tracking results in. Here include the increase FA results. This one is not doesn't pass the FDR threshold. We can just not showing it here. And the second one is a decreased FA that being tested and find it in this longitudinal study. So to test whether there are longitudinal change, you can only do this using the unfiltered database, which include both possibly increase of the FA or decrease of FA. This way allow DSI Studio to test it whether there are real decrease of FA in the patient group. And then one question you may want to ask, can I test it whether there are longitudinal change, but against different groups? So here, instead of just patient group and control group, can I test all of them? But here comes a problem. This database includes both increased FA and decreased FA. So if we tested positive correlation, that could mean increase in the patient group, but also means decrease in the increase in the control group, but also the same as decrease in the patient group. We're kind of missing the increase of FA and decrease of FA here. So if you want to do a group comparison, then the positive correlation could have increased FA missing in here that cause analysis problem. And that's a scenario we want to filter out the increased FA in the database so that when we tested the correlation, the positive correlation won't be also testing the positive increase of FA in the follow-up. And to do so, when we create a kinetometry database of the longitudinal change, if you go to the longitudinal scan, then we will just say filter decrease value in the follow-up. So if you set it this one and click OK, you will see that there's all the value will be just in one side. So all the value is decrease in the follow-up. There will be no other direction of the change. This allows us to analyze whether there are group difference or where there are age difference due to the change. So briefly, just going through each of them. Let me check if there are questions in the chat. There's a question, can you extract connectivity matrices for each subject with a track showing difference? Yeah, you could do it. You could do that. I would say that's a good scenario. Say, if you have a finding, say for example, the one with the results we got here. This one we tested the cross-sectional difference. And then we could see if we can bring in tracks. So let's open the fifth file in DSI Studio and load in the tracks. So this is the track I would say is the generated track of the patient. Then what I could do is I can report it as a connectivity matrix by loading in some of the regions here. And then just following the same structural connectivity report, then you'll get it. But the problem one we usually have is sometimes those findings may not reach the gray matter. So, and in that case, it may not show up in the connectivity matrix. Also, for example, in this study, a lot of findings in the cerebellum in the population, including here, then it's not going to report it. So you really need some tricks to see how you could report it as a connectivity matrix. One way is that you could use this as a C to extend those tracks and to project the possible affected connectivity. Another question, downstream of differential and correlational tractography, when we implement, recognize, and cluster, how is this done? So if we report this, DSI Studio will compare tracks with its building atlas, but sometimes it may not be 100% accurate because here usually only shows up a fragment. When there are neural injury or degeneration, it started as a part of the tracks. So how reliable this could be recognized in DSI Studio, it may not be perfect. So this is a kind of a post-track analysis. Sometimes you just like, if we know the anatomy, I would say this is a middle cerebellum peduncle. This will be reticular tract, or this could be part of the motor pathway. So use an anatomical way to do it. And sometimes if it's difficult, if there are difficulty, of course, we could always go to tract recognition to see if there's a possibility on this could be caudal-spinal tract or other tract. So this just give you a reference. But since this is not the entire track, the accuracy, you may need to have your suggestive decision to see how you can report each of them. And also for the post-analysis, once you get these results, what you could do is you could extract a lot of different things. For example, if we go to step tissue fiber tracking, open the DTIFA database. So in this database, the track showing here is just the template track. But if we set that the finding coming in, then we can run statistic and extract the statistic of each subject from this database. So this is what usually we do. You see that is for each of the subject in this database, is try to extract the value. So once you open the DTI database, loading any tracks and run statistics, you will see it's also reporting each of subject's value in this. And if you pass it to an analysis tool, then you can do the analysis, like compare like control or like compare the good value difference. But if you just simply look at these results, if I just show this as a table, you could quickly see that all the control subject has like the average FA value in this region is like 0.3, 0.3, and then quickly in patients drop to 0.2 or 0.1. So this is pretty obvious. Even before I run any statistics, just look at the values. It's 0.1, 0.1, 0.2, and then the control is 0.3. This is way more significant. So it's a simple way of like post fiber tracking result analysis. You can get this finding. Similarly, you can convert this track to region, and you can report region statistic here. So even within those regions that we have findings, you can get the FA value average. And you see that for the control, it'll be 0.2, 0.2, 0.2, and for the patients, 0.1. So these are all different ways you can blend all different functions within DSI Studio and then report the results. Report the average FA or those significant finding track, or you can separate at different regions. For example, I just want to look at middle cerebral peduncle and then report its results. We can do this. Like we can load in the track and then separate. If I have to separate a specific pathway, I say this one is middle cerebral peduncle. So I quickly set this one, and then I can get a statistic. So this will be the statistic across patient and control, and we can also see the huge difference. So there are all different ways, region-based analysis, track-based analysis, combine all the things all together. So sorry for running over time. Let me see if there are remaining questions I can answer here. If not, I would stop the recording here, and I will stay longer in this meeting room and answer your question. And thanks a lot for participating in this workshop.